Let's go on to hyperparameter tuning. So, as we looked into the previous contents, we've defined what is overfitting. We've looked into basics of regularization, and then we've also looked into hyperparameters. Now, hyperparameters is, in a nutshell, the metaparameters that help the model not overfit. It helps the model to generalize in a better way. Now, when you talk about hyperparameter tuning or hyperparameter optimization, it is the process of finding the best value for a particular hyperparameter. Now, there are two popular techniques available today or that can be used for hyperparameter tuning. One is the grid search, second is the randomized search option optimization. Now, grid search is an extremely simple option. It's one of the most simplest form of hyperparameter tuning. Now, what happens over here is, let's say you have an algorithm. For that algorithm, you have a hyperparameter, and that hyperparameter will be taking a value. So let's say we just simplify this context. Let's say you're talking about the algorithm is logistic regression, and in logistic regression, the hyperparameter would be the parameter C, which is the which is the inverse of regularization complexity. So C is a metric or is a hyperparameter that helps define the complexity of the inverse complexity of regularization. So a higher value will result in a overfitting model, and a lower value will result in an underfitted model. So you need to kind of choose a value which is the optimal one. So it should be, the only rule is it should be a positive value. So you could have a value as 0.0001 or something like 100 also. But then in different use cases, you really can't be sure what is the best value. In some cases, you would say, okay, 0.1. In some cases, you would say 1.2. And in some cases, you would say a 10 or 100. So which is the best one? Like, you don't really know. Now, what is the best method to actually find out the best optimal value for the hyperparameter? It's simple. You try all of them and you choose the best one. So what happens in grid search is, in a nutshell, the same practice. So what you do is you define the hyperparameter, and for that particular hyperparameter, you define a grid of values. So let's say for the parameter C, you define values as 0.1, 0.5, 1, 15, 100, and so on. Now what will happen is it will create a model for each of these values of the hyperparameter, and then it will return the model which has the best accuracy for that respective hyperparameter. So the best accuracy will be measured against using the same defined terms. Let's say you're talking about logistic regression. You could define overall accuracy as your metric, and will choose the best value of that particular hyperparameter for that specific use case. So that's grid search. It's fairly straightforward. You supply the list of candidate values that the algorithm should try, and from that respective candidate list, the algorithm chooses the best one after n number of iterations. N would be the total number of values you provided over here. Now, the problem or the biggest trade-off with this sort of technique is the user must supply the list of values for the parameter. Now, the problem is if you supply a list of candidate values for that hyperparameter, and if unfortunately that candidate list misses out on the most optimal value, then the algorithm will never be able to build the best model. It will only take the values available within that grid. It will never choose the best one. So what happens in randomized search optimization is, instead of passing a grid, you pass a distribution. And randomly, the algorithm, instead of trying the all possible combinations, it will take appropriately in a smart way a couple of different values from the distribution and try that value for this specific hyperparameter. Now, in this process, what happens is, if in case you are not really aware, if you don't really pass the most optimal value in the candidate set, you can still, there's a very high chance that you might actually reach to a conclusion with high accuracy. Your model might actually find the hyperparameter with the most optimal value. So rather than passing a grid of values, you actually pass a distribution of values, and the algorithm smartly takes the most optimal value from the distribution in a smart way. So that's hyperparameter tuning. Two very basic and very intuitive techniques: grid search and randomized search optimization. So that was the last part of overfitting, hyperparameter tuning, uh, and regularization. Let's move on to understand this topic and reinforce the concept with the help of a simple demonstration. And then we move on to the last topic of this module, which is ensemble modeling. So let's move on to Python, where we'll quickly codify and demonstrate a simple example to understand hyperparameter tuning cross-validation.